Hi everybody. This video is about feedforwards in motion control, or how can feedforwards help in achieving a better system performance. Well, this is a classical example of a feedback loop. H is the plant or system which we want to control, and this is my PID type of controller. And at the input of my system, there are also disturbances, and that is mainly one of the reasons why we want to have a feedback controller, to reduce these disturbances which could be present over here, but also in that system, of course. And the physical representation of that system could be something like this: a motor with a kind of a system added to it, and of course an encoder to get feedback to my feedback controller. But in practice, we know a lot of the dynamics of my system. Of course, it's often more than just a motor, and we know these dynamics, so we can use these dynamics in order to design a feedforwards which could really realize a better system performance. Well, how does it work? That's the topic of this video. Let's look to the general approach. Let's say we have that system H over here, and the output of that system is a position X. And the input of my system could be, for instance, a force. So when this is a mass, that force yields to a position over here. And suppose we want to add in software and block in front of that system in order to achieve the following: that the output of my system, the position X, is equal to a set point over here. So what we have to do in software, we have to design and implement a block which is the opposite of that system over here, h to the power minus 1. So this is 1 over h, so 1 over h times h equals a total system transfer function of 1. So in that case, the output is equal to the input. That's the general approach of a feedforward. And of course, in practice, this does not get the real 100% performance over here, because we have tolerances in our system. We did not model everything, so in this software block, it's not really 1 over the system transfer function over here. We could have drift, etc., etc., and of course we could have disturbances added to that system. So in practice, we often have a feedforward branch, which is this branch, which is this system over here, and the output of that feedforward controller is added to the feedback controller over here. So here you see the standard feedback controller, and in addition to that feedback controller, we designed and implemented a feedforward controller over here. And here we see one of the biggest advantages of a feedforward controller. This feedforward controller is completely out of the feedback loop, so it does not has an effect on system stability, and that's really nice. Well, how does it work? How do we design a feedforward controller? We have an example over here. So in this case, I have a system H over here, and the input to that system is a force, and the output to that system is a position X. And we have also Coulomb friction, so friction over here, and of this system we want to design that feed-forward controller over here. So we have said we have to design HFF, the feed-forward controller, as a kind of inverse of that system over here. So how do we do that? First of all, we start with deriving the differential equation of our system. And when this is only a mass which has to be accelerated in order to get a position over here, then we could draw a free body diagram of this system, and we could say that all the forces acting to that body over here equals m times a, so m times the double derivative of the output signal x over here. So my differential equation then looks like this: m times the double derivative of my position, so m times a, is equal to all the forces acting on that system, so in this case on that mass, which is the force F over here, minus the friction force over here, and minus some damping over here, Fv times the derivative of the position, F times the speed, Fv times the speed. notice that Coulomb's friction has been written as a friction constant times the sine of v times the sine of the speed. And that is because when the speed changes from positive to negative, also that friction component has to change. The sign of that friction has to change, because when we drive from left to right, then the friction is in the left direction, and when we go to the opposite direction, the sign of the friction has to change. So this is my differential equation of my system over here. Next step is that we have to linearize that differential equation. Or in other words, we only want to have signals which are equal to the input signal and the output signal. So we leave that part of my differential equation out of my linearized differential equation. And then we get m times the double derivative of the position is F minus the Coulomb friction component times the speed over here. So that is it. And then we can transfer this differential equation towards the S-domain, and we can derive the transfer function of that system with x, the position, as an output and the force F as an input. So we can replace ddt by s, so we get s squared over here, and we get an s over here. And then we have x as an output, f as an input. So the transfer function h, x is x over f, which is equal to 1 over ms squared plus fv times s. That is the transfer function of my system h. So when we have that, this transfer function, we can say the feed forward has to be the opposite transfer function of this transfer function. So the opposite of this transfer function h. The output of my feed forward is my force over here, the feed forward force, pardon me, and the input is my set point over here. So we can say the transfer function force over set point position here is the opposite of this transfer function, so it's the opposite of this transfer function. So it's equal to ms squared plus Fe times s. So my feed forward transfer function again is m times s squared plus Fe times s. So we can now realize a differential equation out of this transfer function in order to implement that feed forward. So how do we do that? Well, we replace again s by ddt, so we now can say that the output of my feed forward controller is equal to m times the double derivative of my set point position, so it's m times my acceleration set point plus Fv times the derivative of my position set point, which is equal to Fv times my set point in speed. So this is my differential equation, which I want to implement here in software, because this, of course, is software and this is my real life system over here. So I have to realize this in software. And again, notice at this moment we did not include my Coulomb friction because I had to put it away in order to realize a transfer function over here. So what we can do now is, first of all, we define the M, the FV, and the FC. Because in practice, what we want to do, of course, is we want to set this mass in my feed-forward control here in software as accurate as possible to the real mass of my system. But we do not know every mass in the system, because we do not know every mass of every bearing or every pulley or even every transport belt which is in the system. So the mass in my feed-forward controller is kind of an estimate of the real mass over here. And that's the same thing with the damping coefficient Fe, of course. So we use M accent instead of M and Fe accent instead of Fe. And of course, we also are going to do that with the Coulomb friction over here. So in practice, in my feed-forward controller, these coefficients are not 100% the same as the real masses, dampings, and frictions in my real life system, simply because I do not know them 100% exactly. And of course, keep in mind that when my real life system starts to move and is in operation, then these values might slightly change. And when you make a lot of systems and you have only one feed forwards in software, then of course also there could be tolerances on my mass. So these are estimated values. So now again, I can transform the differential equation of my feed forwards to this equation, which has at the output of my feed forward controller, the F equals the estimated mass times the double derivative of my set point over here. So this is my acceleration set point, plus my estimated um, damping over here times my speed set point over here, which is the derivative of my set point, position set point over here, plus the estimated Coulomb friction times the sine of my speed set point. So we have a acceleration contribution, which we call FFM. We have a speed contribution, which we call FFV, and we have a friction contribution over here. So we have a feed-forward controller with three parts: an acceleration part, a speed part, and a Coulomb friction part. Well, let's implement it now in a block diagram over here so we can implement it in software. So here we have our estimated friction, my estimated mass, and my estimated damping over here. What we are going to do is we put to the input the appropriate signals which we defined in the differential equation of my feed-forward controller. So the input of the control of my Coulomb's friction is the sine of my speed set point. The input of my mass is the set point acceleration, and the input of my damping coefficient, so the estimated Fv, is the speed set point. And the outputs of these three parts are added all up and added to the output of the feedback controller over here. So now we have a block diagram in how we could implement that feed-forward controller. Remember, this is all software and this is my real-life system. So now we have to connect this feed-forward controller to my set point over here. So one more thing. Suppose that in real life you had, for instance, an amplifier which amplifies the voltage towards a force, a current, and then a force, which is the input to your system. So when a servo amplifier is in real life at this point in your system, so this is hardware again, then you have to multiply all the feed-forwards parts with 1 over that servo amplifier, 1 over that Ka gain, in order to make this as much as the inverse function as possible over that system transfer function over here. So you have to take that servo amplifier gain into account. So this was my block diagram, and now I have to add my set point to it. And remember, when we have a second order differential equation, what we call a second order motion system, so we have a second order feed forward over here, we need at least a second order set point. And a second order set point means that the double derivative of my position should have a constant value, so no infinite values over here. And I can realize that by having a trapezoidal speed curve over here, which implies that my acceleration is constant in this part and it's 0 in that part. So then in that situation my speed is constant, and a deceleration part over here. This is the easiest way of implementing a second order set point. When you want to have more information about set points, please look to the video about set points in motion control. But an easy way of designing and implementing this second order set point is by defining your acceleration profile over here. So a constant acceleration over here, a 0 acceleration in this time, and a constant deceleration in this time. And when you have implemented this acceleration, you could integrate it, and then you get the speed curve over here, the trapezoidal speed curve, and then you integrate it once again, and you have the S-shaped position set point. So now we connect the acceleration to this feed forward. We connect the speed to this feed forward, and we connect the position to the input of my feedback controller. And of course, the sign of the speed should be connected to this input. So now we have the real feed forward system ready. So now we can have a look how it functions and what the benefits will be. So I made a simulation. So this part of our simulation is my linear motion system, which I discussed earlier. So it's mass with viscous friction and Coulomb friction over here. So this is the model of my real process. And I have designed a feed-forward controller appropriate to what we discussed earlier, and this is my feed-forward controller over here. And this is my second order acceleration set point. So with a constant acceleration, a zero acceleration, and a constant deceleration over here. And when I integrate it once, I get my speed set point, which will be connected to my feed-forward controller over here. And when I integrate it once again, I have my position set point, which will be the input of my feedback system. And in that feedback system, I have implemented a PD controller with a proportional part over here and the derivative part over here. So this is all software, the set point, the feed forward and the feedback controllers, and this is a model of my hardware. Now I'm going to look how the system behaves when I only realize feed forwards, when I only realize a feedback controller, and when I add the feedback and the feed forward controller as a combined input to my system. Well, let's have a look to the simulation results. In this graph, we have only used a feed forward, so not a feedback controller, and we put the mass 10% lower than the real mass. And what we see is that we have quite a good tracking performance, but at the end we have an offset over here because we do not have a feed forward controller in this situation. But the tracking performance, well, it's quite nice. When we do the same with the friction feed forward, we set the mass to the nominal value, and we set the friction in my feed forward controller lower to the actual friction. We see even better tracking performance, and at the end we still have an offset, an end error over here. When we only use a feedback controller, you see that, well, in the end situation, we have a very good performance, but the tracking behavior is rather bad because you see a big error between the set point over here and the real position over there. Well, and when we combine feedback and feed forward, we have an excellent tracking performance, and we have an excellent end position over here. So a really low error also in steady state. So, well, what we have seen is that a feed-forward controller really helps a lot in achieving an excellent performance, and it's very easy to implement. That's all. Thank you for watching to this video.